So I'm going to be talking about methane and specifically how we think of it in relation to carbon dioxide and what we might oversimplify from our current kind of mental picture. So I'll briefly discuss greenhouse gas emissions from livestock, especially ruminants, emphasizing why methane is a big deal, then think about how the impacts of methane relate to carbon dioxide and how we communicate them as carbon dioxide equivalents, and then think with this knowledge, how do ruminants actually contribute to global warming, and then try and move on to some overall conclusions and bigger picture implications. So I'm sure most of us are familiar with what processes generate greenhouse gases from livestock production, but to remind us, here's a simple picture, and it's important to emphasize that in most agricultural production, and especially livestock production, the biggest source of emissions are the direct on-farm production stage. And for ruminants, the thing that makes them stand out so much is that we have so much methane emitted, and that's largely directly from the animals from enteric fermentation. So the ruminants are eating grass or other plant material, digesting it, and then breathing out methane as a byproduct. Of course, we also have some methane lost from their manures, and we have nitrous oxide lost from the manures or from agricultural soils from organic or inorganic nutrient inputs. So that's the on-farm emissions, which is the biggest part of the carbon footprint. But if we want to follow the whole supply chain and think about what other emissions is that production system responsible for, we need to think of the pre-farm emissions. So any energy use CO2 from embedded production emissions, so particularly fertilizer production, as it's very energy intensive. But then for any off-farm feed import, any embedded emissions in producing the feed, so nitrous oxide from applying the fertilizers there, carbon dioxide in agricultural operations, and particularly carbon dioxide possibly from deforestation and land use change. Transporting various inputs from point of production to the farm is also going to generate fossil fuel CO2 emissions in transport, but I want to briefly note that food miles and transport emissions tend to be overblown in this kind of debate. So the transport element of the emissions footprint is not a very large consideration. So we have all these emissions, and then we would combine them into a single carbon footprint and then typically express that per unit of milk or meat or whatever the output of interest is. So what does a typical ruminant carbon footprint look like? Well, this is from a paper a few years ago looking at average lowland sheep production in England and Wales. So per kilogram of finished lamb live weight, it was about 10 kilograms of carbon dioxide equivalent, and almost half of that was from methane, and most of that methane was directly from the enteric fermentation. There was still significant contributions from nitrous oxide and direct CO2, so I want us to keep that in mind during the talk. But because ruminant footprints are so dominated by methane, so here it's about half, but typically between a third to two-thirds of the carbon footprint, discussions about the sustainability of ruminants, and especially their climate impact, have been dominated by valuing methane. But what is a carbon dioxide equivalent? So it's what we use for most emissions reporting or policy design, including in the previous talk, and I'm sure we'll see more later. So it uses this metric called the 100-year global warming potential to scale emissions of different gases relative to carbon dioxide. So it's relative to carbon dioxide. Carbon dioxide is worth 1. Nitrous oxide has a global warming potential over a 100-year period of 265, methane of 28. This is from the most recent IPCC assessment report. These values are also updated over time, so it was smaller in older assessment reports, still used for our national inventory reports. I will warn the audience now, it's almost certainly going to increase again for methane in the next IPCC assessment report. But if we use this, it would say, if my farm is emitting 1 ton of methane per year, then I'd simply times that by 28 and say that was the equivalent of 28 tons of carbon dioxide. So it's essentially assuming that all greenhouse gases affect the climate in exactly the same way, just more or less strongly, because it's a single scaling factor. But I will argue that it overlooks some important differences between the gases. Now, before I get into that, I want to emphasize methane is still very important. I don't want anyone to leave this presentation thinking I've suggested otherwise. So compared to CO2, for any one molecule of methane in the atmosphere, it's actually having a much greater warming impact than carbon dioxide. Overall, it's the second biggest contributor to our current elevated temperatures, second only to carbon dioxide. And the trajectory of methane concentrations in the atmosphere is tracking closest to our worst case emissions scenario. So the figure on the right is showing the bottom curve is where we hope to be in our ambitious mitigation scenarios, where we'd already be on this declining atmospheric methane concentrations. The dashed line in the middle is kind of business as usual, and the top line is the worst case if we made no efforts to mitigate emissions whatsoever. And the observed concentration of methane seems to be tracking this worst case one. So we do need to take it seriously, but most importantly, we need to accurately value the effects of this methane. I'll briefly note that it's not entirely clear what the main cause of this continuing increase in methane emissions are. It appears largely due to agriculture because the signature is that it's biogenic of origin, but it's also from fossil fuel methane emissions, and we can't specify exactly what the main causes are. Not at the moment anyway. So what are the big differences between carbon dioxide and methane? So there's been a lot of work on this. We can get into many details afterwards if there are questions or if anyone wants to come and see me. But fundamentally, it's actually a very simple difference. So carbon dioxide, any CO2 that we emit today, a large portion of it will stay in the atmosphere for millennia unless we actively remove it. So from any normal policy-making perspective, we release CO2, we can think of it as altering the climate indefinitely. For methane, it has a natural atmospheric lifespan of a couple of decades. So even though it's a stronger greenhouse gas, this very pronounced difference in their atmospheric lifespans means they have extremely different dynamics and affect the climate very differently. So this can be summed up simply by emphasizing that we have to think of carbon dioxide as a stock pollutant, whereas methane we should think of as a flow pollutant. So what do I mean by this? So this is summed up very simply in this figure. So if we imagine on the left side, we have constant emissions each year of the two gases. For carbon dioxide, emissions are staying the same year on year, but because it's adding cumulatively, each new year's CO2 emissions added on top of the last ones. So the concentration of CO2 of the atmosphere, even for constant emissions, is going to be accumulating and will increase. For methane, if we manage to keep emissions at a constant level, and bear in mind they're increasing at the moment, so this is an ambition, it's not where we are, but if we did manage to keep methane emissions at a constant level, then we would eventually reach a position where natural atmospheric removals are balanced by those emissions. So the amount of methane in the atmosphere and its major climate effects depend on the current emissions rate. So it's a flow of methane that determines its climate impacts, whereas the amount of CO2 in the atmosphere and its climate effect depends on the total accumulated stock that we've ever emitted. So if we try and collapse them to a single methane is the same as carbon dioxide but stronger, we will lose this important difference in the dynamics and misunderstand how the two gases lead to global warming. This doesn't mean we can ignore methane, of course. If we imagine, what if we finally manage to get to zero emissions of either gas? Well, if we stop CO2 emissions, then the concentration will be stuck at that elevated level that we'd reached from all the past emissions until we finally cut them out completely. So we have to reach net zero CO2 emissions, or we will always have further warming. For methane, of course, if we decrease emissions, it's still good. And because they break down quite quickly, decreasing emissions means that the atmospheric concentration would fall after that, and we'd be able to reverse a significant amount of the warming that we experience from it. So it's not to suggest that we shouldn't also be trying to decrease methane emissions, but if we do so, it's having a fundamentally different physical impact from decreasing CO2 emissions. So to try and summarize some of those points, to emphasize again, bringing CO2 emissions to net zero is non-negotiable. It's a physical requirement if we have any desire to stop ever-increasing warming. But for methane, because it depends on the ongoing flow, we don't have this same physical necessity to completely remove emissions. It would be possible to have some ongoing methane emissions compatible with a stable temperature limit. Decreasing methane emissions is probably still good, and it's probably required to meet our 1.5 or 2 degree temperature targets, because the amount of warming we're committed to, again, is driven by the current ongoing rate of methane and the cumulative total of carbon dioxide. We don't anticipate we can cut out carbon dioxide quickly enough that we will be able to reach those targets through acting on carbon dioxide alone. We probably have to also reverse some of that methane warming to get to these ambitious temperature targets. But what those trade-offs are, how much warming from methane should we reverse versus stopping extra warming from carbon dioxide, that's not physics, that's a policy decision. We can illustrate what the actual physical dynamics are, but the choice of those mitigation trade-offs is not something we can define as environmental scientists. But I would hope that policymakers will be aware of the physical differences and recognize implications such that if we ask all sectors to reach zero emissions, we're asking CO2 emitters to have a physically quite fundamentally different role in mitigation than we would for methane emitters. So that's the policy and the metrics, but there is, of course, a physical reality of the climate change we experience. So outside of talking about what percentage of emissions are from agriculture or so on, what if we simply model the warming from direct livestock emissions? So that's what this paper from a couple of years ago did. So the figure on the left is showing our temperature change as observed to the present day, and the bands across the top are showing what was the contribution of that temperature change from direct livestock emissions of the different gases. So the largest blue band at the top was direct livestock methane, the smaller red band is direct livestock nitrous oxide, and the green band is direct CO2 from pasture conversion. So as of 2015, I think, is when they went up to. This band is the actual proportion of experienced global warming from direct livestock emissions. So it's about 0.2 degrees, about 20% of the 1 degree of warming we experience. So we have to acknowledge, yes, livestock are responsible for global warming. We know how much, it's a physical reality, but this is the real dynamics of it. And in fact, it was probably in about 1950 that was the biggest proportion of total temperature change, because since then, we've had ever ongoing and in fact increasing rates of CO2 emissions from other sectors, adding to this big grey section underneath. So if we project that forward over the next century, what happens to the overall climate and the share of warming from livestock if we do or don't try and make any different mitigations? So on the right-hand figure, this top line, this is our worst case scenario where we don't try and mitigate any greenhouse gas emissions. So we keep on increasing livestock emissions, but also we keep on increasing and sustain our fossil fuel emissions. So we will still have warming from livestock, but because we haven't cut out the CO2, the share of warming they're responsible for is increasingly small. I'm not saying that we shouldn't follow around them, but if we don't get CO2 sorted out, it's increasingly irrelevant what we do with other sectors. Whereas this other more ambitious one, RCP 2.6, that keeps us under 1.5 degrees, this is if we cut out all fossil fuel emissions by mid-century, and we reduce, but we don't have to completely eliminate livestock emissions. So the bottom scenario is where we need to be. We're a long way from at the moment. The highest annual fossil fuel emissions were last year. We're still increasing fossil fuel emissions. We need to get that sorted before any acting on livestock is of overall consequence. So to try and bring some bigger picture messages, first I want to remind you that methane, as we saw in the footprint earlier, was not the only gas associated with ruminant production. CO2 and nitrous oxide are longer lived, so they still act cumulatively, and we still need to reduce and offset them. And given the unique importance of carbon dioxide, as I think I've emphasized, land use and CO2 emissions from deforestation, or the missed opportunity of not using land use for carbon dioxide, are potentially actually the bigger issue for livestock and the climate, even though we seem to have focused on methane from both sides of the debate. And then obviously there are wider environmental issues that we might also overlook from focusing on methane. So nitrates, as we heard about, ammonia, various other issues we brought in. And then obviously we have to balance those about the positive outputs from livestock systems, landscapes, the cultural value, rural economy, and not forgetting that we have them in the first place. An element that is getting lost in the debate is, I think, whether people are advocating for positions of livestock sustainability, and I think there is a space for sustainable livestock production, probably smaller than it is at the moment. I would agree with Baz on that earlier. But that's a different argument from whether it's an environmentally optimal decision to have livestock in the diet. And this is, again, it's not a physical or an environmental science question. This brings in wider debates about what activities we want to continue doing in the face of climate change. So to summarize, I'd say it's worth getting methane right, and at the moment, we're not really doing that. We have a simplified and in some respects misleading way of thinking about it. But from both sides of the argument, methane is also only part of the story, and if we focus on methane at the detriment of these other issues, we will lose sight of wider environmental issues and also not engage with the positives of livestock production that we might also want to talk about. So thank you very much for your time.
Thank you, John, for this talk. We have time for one or two questions.
Sorry for jumping in, but one policy maker left, the other is still in the room. For me, what you say is extremely important in terms of the concrete policy implications of what we're doing. Because if we're to limit methane, there are two ways of doing it. One is through the cattle and sheep sector, where there is a direct and indirect policy impact. And then there is through the other type of meats, where we don't have even an indirect policy impact. It's pork and poultry, which are, by the way, the ones that are increasing in much higher rates than the other ones. So my question is, from all these impacts of methane, do you have any sense how much of this is coming from feed, or if, to put it the other way, feed improvements? How much could they contribute, and how much is land use based?
So the methane is almost all directly from the animals, and this is what makes the ruminants so unique. But what I want to emphasize from the last point there is that if we focus on climate change mitigation through methane, because it looks like it will be an increasingly large share of emissions in the future as we decarbonize, we might lose sight of actually bigger issues to do with feed production and embedded CO2 emissions for ruminants, but maybe even more for pigs and poultry. So I do want us to decrease methane emissions, and policy should also strive to do that. But if we have a misleading impression of it, then I think we risk losing sight of the other environmental impacts, including the other greenhouse gas emissions. And because we haven't really been switched on to these nuances, it's actually quite hard for me to give a definitive answer as to what's climatically beneficial. Is it still to decrease ruminant numbers anyway and increase pork or poultry? I don't know, because if we just report things in a total carbon footprint that assumes they are the same, the temperature implications of those decisions are not immediately clear. So I think we need further research and more holistic frameworks to balance those trade-offs.
Thank you for the very interesting presentation. Tiago Domingues from Terra Prima. Although I agree with your message that methane is small compared to all other things, and especially the rates at which it's changing and CO2 is increasing, I do think that the picture you're giving of methane as a flow pollutant and CO2 as a stock pollutant is misleading. And misleading for two reasons. Well, the first one is they are in fact both stock pollutants. What differs is the scale at which they are stock pollutants. So methane is maybe stock pollutant at a scale of 10 to 20 years, and carbon dioxide 100 to 150 years. So I think that's the first...
it's a millennial scale, so I think it is
It's
really
not millennial. The half-time of CO2 in the atmosphere is around 150 years, but to keep going. So that's the first issue. And the second issue is you cannot also ignore that, that methane, even while lasting 10 or 20 years, is heating the atmosphere and hence heating the oceans. And the issue is the effect of heating. Climate change happens, in fact, and people should be aware of that, because greenhouse gases heat up the atmosphere in the first place, but where that heat gets stored is, in fact, in ocean heating. To use the terminology of stock and flow, in fact, heating the atmosphere itself is flow. What is stock is when you heat up the oceans, because it's heating up the oceans that will keep the atmosphere warm. And so if you have methane there for 10 or 20 years, it's still going to heat the oceans. And so it's still going to contribute to future climate warming. So 2 points. Methane is a stock pollutant, but on a smallest timescale. But in fact, the real timescale on which it is a stock pollutant is longer than you are transmitting because of the effect on the oceans.
Yeah, so I don't dispute the point that there is also the long-term climate response to emissions. And this is a very simple picture of it. In our actual metric work, we do now incorporate that longer-term component of the response to methane. But I don't agree with you about the half-life of carbon dioxide. Unlike the other gases, it does not have a simple exponential decline with a meaningful half-life. A significant portion of emissions will remain in the atmosphere for tens of millennia at least, is the understanding from all of the geophysical models. So I think from any normal human decision-making perspective, it does make sense to think of it as an indefinite stock pollutant. And I can pass on various papers to point that out to you if you want.
Thank you for this nice presentation. And just for I think what is might be a misunderstanding between your answer as a question, I do agree with you about the sort of millennium time scale for the stability of CO2 in the atmosphere. But in fact, we should also remember that we have carbon sinks. So we have oceans and we have the terrestrial biosphere, which uptakes parts of the CO2. So in fact, you are not talking about the same thing. I think the question was about, is the CO2 not uptaken after some stage? And this happens, in fact. And your question was about the stability of CO2. This is just to clarify that matter.
Yes, but a significant, despite all the uptakes, a significant fraction of the CO2 does remain in the atmosphere essentially indefinitely. And so again, back to the past question, for CO2, we still have those same lagged climate responses of ocean warming. But unlike methane, we also have the gas still in the atmosphere, still exerting an ongoing warming effect. So I think if you want to understand the dynamics, and especially the long-term dynamics, you do really need to separate them into those different time frames.
Okay, thank you again.